Chapter 5, Sampling Distributions. First up, what is a sampling distribution? We know that the process of statistical inference involves taking statistics from a population to draw conclusions about that population. It doesn't make sense to sample every single individual in a population if we're trying to learn something about that population. So instead, what we like to do is take a smaller sample and use that sample to make an inference or a prediction or an estimate about that population. We also know that because of this process, any two individuals performing that sample could get different results. Furthermore, it's important that we understand the differences between parameters and statistics. So a parameter is a number that describes some characteristic about the population, and a statistic is a number that describes some characteristic of a sample. So when we take statistics, when we find a mean or a proportion for a sample that is a statistic, we use it to predict a parameter from the population. Um, just some symbols that we use for population mean, we use mu typically, whereas for sample mean, we use the x with a line over it, or x bar. For population proportion, we use a italicized p, whereas for the statistic, p with a hat over it, the caret, literally call it p hat. We talked about that a couple units ago. That's what we use to talk about the statistic. Then for population standard deviation, we used the sigma, the lowercase sigma, whereas we'll use just the lowercase s for a sample standard deviation. That's the big difference, those terms. Now, like we said just a second ago, x bar may not be that accurate of a representation for mu. Different people taking different samples may get different results. So, if I perform a survey, a bunch of people at the school to figure out what their heights are, and I take, 30 different random students, I'm probably going to get something different than somebody else doing the exact same process, taking random people and measuring their heights. Even if we have a decently large sample size, we'll still get different results. I mean, it's just unrealistic to think otherwise. And the truth of the matter is, neither one of them will be precise. They'll be, neither one of them will be exactly correct, right? Both of them will probably be close. One of us could be way off, who knows? That doesn't make either one of us right or wrong. It just means that the, we have variability in our sampling. So sampling variability is the notion that any two people are going to get different results when they do the same statistical process. And this is very common, and it's unavoidable, unfortunately. So one of the things that we do to sort of mitigate that is we look at the sampling distribution rather than just a regular distribution. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In other words, if we took one of the possible samples of size n, so let's say size 30, and we found all of the different possible sample proportion or sample means, and then repeated this until we had all possible combinations, we would have what is considered a sampling distribution. And of course, this is something that is not really realistic to carry out. So instead, we use simulations to imitate the process of taking, or we will just simply take a whole bunch of samples. So in theory for this, if we took the 2,000 something students at our school and we took every single possible combination of 30 students and got their average height for that sample, if we took all possible samples, of course there would be millions of possible samples. I don't know about millions, but if we looked at all of those possible combinations, then that would be considered a sampling distribution. Here's just a visual of what we were talking about. So this is I can't tell what that is. I don't know what this is supposed to represent, but it shows that, there's, let's say, red and blue marbles in a bag or in a jar. 100 of them are blue, 100 of them are red. You're taking samples of size 20 each, and then you're measuring what proportion of them are red versus what proportion of them are blue. It looks like in this case you're caring about what proportion of them are red. So one sample could be, you got 8 out of the 20 were red. The next sample you could have gotten, what does that say? 11 out of the 20 that are red, and so on. And all possible combinations of this would give you a distribution of the different possible proportions. So you see that, the amount of times that they were exactly, half and half was the largest, and then of course on either side it teeters off until you have, some very unlikely combinations. Now, when we describe sampling distributions, we use the same terminology that we use for any other distribution. So we care about the center, the spread, and the shape to determine if they're trustworthy representations of the population. So here we have the sampling distribution from before. This is a whole bunch of different combinations for sample data. This is, of course, a simulation. Unrealistic to do this a whole bunch of times. But if we're looking at the same distribution, we notice that, one time we had, only 0.15 or 15% of the marbles out of the 20 were red. So that would have been 3 out of 20. A whole bunch of times we got 10 out of 20 red marbles. Looks like maybe 1 or 2 times we got 18 out of the 20 marbles were red, and so on. So more often than not, we got half of them red, and then of course, it teeters off or peters off on either side. So notice that the mean of this distribution is right at 0.5. And notice originally exactly half of the marbles were red, or in other words, the true proportion was 0.5. When we get a scenario where our sampling distribution provides us with a distribution whose mean is exactly what it's supposed to predict, in this case, the mean of this distribution is telling us that the proportion of marbles that were red the most often was 0.5. Since that is true when compared to the actual population distribution, half of the marbles were in fact red, we can refer to this as an unbiased estimator. Basically, a sampling distribution where the mean of whatever statistic we were gathering provides us with a good prediction or a precise prediction of whatever it was we were trying to predict, then we call that an unbiased estimator. Next, we look at the spread for a sampling distribution. So obviously, when we look at what we had up here, getting a sampling distribution whose mean, whose center is very accurate, it's right where we want it to be, that's a very good thing. But sometimes that's not necessarily enough, right? Sometimes, that's still not all that trustworthy. We see here that, we actually do have a lot of outcomes where the proportion was 0.45 or the proportion was 0.55. So maybe we'd be thinking, well, maybe it's possible that maybe we would be thinking that there's 110 out of 200 marbles that were red, or maybe we would be thinking that there was 90 out of 200 marbles that were red, because those two are pretty close as well. So what we can do is reduce the spread, and there's an easy way to do this. If we take large samples, then what that'll do is reduce the variability. And there's a very good visual that I'll show in the next video about how this works. But if I were to show you, if someone's come along and say, hey, the proportion for this is 0.37, and I have proof of that, it's this graph, and they showed you this graph here in green, you'd say, okay, yeah, I mean, that's pretty good. But if someone came along and said, hey, the proportion is 0.37, here's the evidence here in this graph, you'd be like, okay, yeah, this one is very clearly that's 0.37. It's right there. It's the only one where there's a lot of them. So it would make sense that this one would be a little bit more trustworthy. That's kind of what this is getting at. And again, I'll show you a visual here in a second. So bias means that your aim is off. If you're getting something that is biased, it means that your center is not where it's supposed to be. Since the proportion here, since the true proportion of red marbles here is half, if we were getting a sampling distribution that was telling us the proportion of red marbles was something different than 1/2, then our center would literally be in the wrong place. Basically, something would be off. And the only way that that would happen, realistically, when you think about it, is if our sampling method was incorrect. So if something we were doing in the process of trying to randomly draw marbles out of a jar was somehow not random, then that would mess up the results and we would get skewed results. So if that were to happen, then we'd have biased results, hence the name bias, just like it was in unit 3, right? So that is visualized here by, being off target. If you're off target consistently, but you're hitting the same spot, it means whatever the thing that you're using to aim, something is messed up. If you think about, shooting a BB gun at a target, if you're aiming at the target and you're constantly hitting the same spot, but it's off center, then there's something wrong with your BB gun. If you have a high variability, that means you're aiming right at the target, but you have a whole lot of spread. This isn't all that bad necessarily, because it's still centered where it needs to be. So you still know that you're getting close to the right place, but in reality, you would like for things to be a little more centered. So when that happens, you can fine tune what you're using to shoot. You can fine tune your BB gun and make some minor adjustments on your tool, if you will, and you'll hit the target more precisely. Now, reviewing the central limit theorem. So this again was something that we touched on in Unit 1, and a lot of the themes from Unit 1 are going to come back. So central limit theorem tells us that basically if we take enough samples, if we do a process enough times, then it will predict or it will approach the theoretical mathematical value for whatever it represents, right? Now, we're going to get to see this in practice here in a second because most population distributions are not normally distributed. That's just the sad fact. Normal distributions are easy and they're convenient to work with, but unfortunately, most of the time, things that we deal with are not actually normal. But when we increase our sample size, as we'll see here in the next video, no matter what shape the population distribution is or has, the sampling distribution will approach normal no matter what. So if the population is not normal, central limit theorem tells us that it will be, provided that the sample size is big enough. Now for means, it's easy to remember because it's about 30, and for proportions, it's a little bit more complicated. It's usually if you have at least 10 successes and 10 failures. But we'll see how that pans out here in the next video.